Welcome to the lecture series, Earth Materials for a Sustainable and Thriving Society, sponsored by UNESCO's International Geoscience Program. For more information about the series, please visit bit.ly/UNESCO Lectures. This lecture series has been organized by the Irish Centre for Research in Applied Geosciences and the International Union of Geological Sciences. A special thank you to the Jeju Province Development Corporation from Jeju Island of the Republic of Korea, who provided support to UNESCO for this series. We would also like to acknowledge our media partners who have promoted this lecture series around the world.
Hello, my name is Larry Meinert, and I am pleased to be the first speaker in the UNESCO Lecture Series on Earth Materials. I will start off with some general concepts about mineral resources and how they are essential for economy and society and in support of the United Nations sustainability goals. I think most people are familiar with the 17 goals. All of them are important and laudable. And what's fairly important is that every single one of them requires mineral resources to move towards successful implementation. And so I won't be looking at the policy as much as the actual mineral resources that contribute to these things. And if we start off at a very basic level, we have three general forces in action here. The three curves on this diagram, the green one is the world population for the past 100 and something years. And you can see that since 1900 up to the present, world population has grown by about 4 times. In addition, each one of those people is now consuming about 6 more times material resources per capita than they were 100 years ago. Okay? And the top curve, and all these curves are for copper, but I could do it for any element in the periodic table, and the story would be roughly the same. And so the blue curve is for total production, which is basically the combination of higher world population and higher standards of living, and resulting in 22 times more production of copper than 100 years ago. And none of these trends look like they're slowing down, and this is just a fundamental thing that we need to come to grips with, driven again by population increase and rising standards of living. Okay, we could ask, well, who needs mineral resources? And the short answer is everybody. Okay, this is a slide for American consumption, but I will show how it relates to the rest of the world as well. Every American born needs 3.2 million pounds of minerals, metals, and fuels in their lifetime. This is an immense amount of stuff. Okay, the various little graphics illustrate how much copper and gold and lead and salt and stone and gravel and zinc are needed. But one way of illustrating this is to compare it to China for one commodity. This is cement. And this is an amazing statistic. In the last 3 years, China has used more cement than the United States did in the last 100 years. Okay, so this is a graphic illustration of those curves I showed you gradually rising due to population and standards of living. Okay, and when you think about this, 100 years in U.S. history is the development of all of our interstate freeway system, the major cities of New York, Chicago, Los Angeles, all the buildings, all the infrastructure. And in 3 years, China has used more cement than the United States did in 100 years. They say a picture is worth 1,000 words, so let me show you this in pictures. Here is the city of Shanghai, one of the major cities in China, in 1987. And the next slide is the same view, the same city in 2013. Okay, you can see there's an immense amount of building going on, and this accounts for most of what I was showing you in the previous graphs. Tremendous increase in the amount of almost all materials. The last graphic was for cement, for copper, but all those buildings require lots of materials, and this is what is going on worldwide. Okay, this obviously raises the question of, well, do we have enough materials to actually do everything we want to do? And people have worried about limits to growth or running out of resources. And one thing we need to make very clear, we are not in danger of running out of resources. And the various studies, such as the famous limits to growth study in the 1970s, were based on a misunderstanding of resources and reserves. What they basically do is they take reserves, which have a very specific meaning in terms of being drilled out and known exactly what is there, and then compare that to how much is used every year, and assuming that, well, when it's all used up, we're done. It's all gone. And that's not true, because reserves are not the same as all there is. Okay, the models are claiming that they're looking at all there is, when in fact they're looking at a very small subset, which is legally defined reserves. And to greatly simplify this, when companies have a new discovery and they determine how much copper or zinc or iron might be in it, they do that based upon drilling, and they drill out as much usually as they plan to produce in 10 or 20 years. It's simply not economic to drill out what might be needed for the next 1,000 years or 5,000 years, because it costs money to do that drilling. So reserves will always be a small fraction of what's actually there. And here's one of the ironies. Reserves are increasing every year. The reserves now are larger than they were 20 years ago. The reserves 20 years ago were larger than they were 50 years before that. And the reserves 10 years from now will be larger than they are now. So it's not that we are running out of resources, but there are legitimate concerns about the consequence of use of those resources, and that's a separate issue, and the possibility for disruption of supply chains for those resources. Okay, we're seeing this play out right now with carbon dioxide as the result of consumption of hydrocarbons, of energy. And so it's not that we're running out of hydrocarbons, but the consequences of use are now creating problems severe enough that we may well shift as a global society to other types of energy. And that may well happen for mineral resources as well, but it's not driven by running out of the resources. I went through this in some detail in a recent paper, trying to lay out exactly what resources and reserves are. Not that we need to understand that in detail, but you do need to understand that the various models that claim that we're going to run out in 10 years or 20 years or 30 years or 50 years simply are not based on facts. Okay, so how are minerals important? Okay, they're used in almost everything: cars, refrigerators, TVs. Every commodity of modern life contains mineral resources, and their use has changed dramatically over the years. Here's one illustration for the type of smartphone that almost everybody in the audience probably has in their pocket. Okay, and the new one on the right uses more than 75 elements, almost the entire periodic table. Okay, usually in very small amounts, but each one of those elements is critical for the function of that device. And this is a change from the old telephones. Those are old enough to remember the original cell phones, and of course landlines before that, which also used lots of mineral resources, but nowhere near as much as modern technology. And again, what's really important is that some of these use elements that are used in very, very small quantities, okay, grams or micrograms, but that each one of those elements is necessary for the function of the device. So if you don't have that element, then the device simply won't exist. Other important uses of mineral resources are going to expand in the future. Alternative forms of energy. Renewable energy, such as wind turbines, require large amounts of various elements: iron, copper, molybdenum, and things called rare earth elements with very strange names like neodymium. Okay, solar cells require lots of elements that are used in very small amounts, but again, they're critical for function, things like cadmium and tellurium. So all this means is as we move to better technology, to more efficient technology, it's still going to require mineral resources to drive all of that. As we go to electrify the vehicle fleet of the world, starting with cars and trucks, but expanding to basically everything that moves around, we're going to need even more of these various elements. And again, what's important, some of these are fairly rare elements: ytterbium, europium, and each one is essential for some part of the functioning of this device. So as the world changes in terms of what we do and how we build it and we innovate, we're still going to need mineral resources, and most likely we'll need some mineral resources in greater quantities than we used to, because we weren't using them nearly as much as before. Okay, so this then raises the question of, can we reuse some of these things, okay, through recycling or innovative manufacturing? And the answer is absolutely yes, we can and we should, but, and this is a very important point, okay, we'll never be able to get enough from recycling, because world population is growing and standard of living is increasing. So if we held everything constant, Okay, nobody got to improve their standard of living, and there was never another person on Earth that wasn't already here. Then we could get by with recycling if it was 100% efficient. Okay, one, it'll never be 100% efficient, and two, we're always going to need new material because we're going to have new people and we're going to have hopefully rising standards of living. This doesn't mean we shouldn't do recycling. We absolutely should, and we should do as much and as efficiently as we can. But there's some realities we need to understand. And one of them is that a lot of the elements in various devices, particularly modern electronic devices, are very difficult to impossible to separate out, at least economically. This graph illustrates this, looking at the value of the commodity on the vertical axis and how many different steps might be necessary to get it out. In other words, basically how much is there that we can extract on the x-axis. And the colors range from 0 recycling to 100% recycling. And there's a arbitrary dash line going down through the diagonal where things above and to the left of that line have enough value and are simple enough that we can have efficient recycling. So some things like automobile batteries and cans and bottles are very, very easy to get very close to 100% recycling, even though it requires energy, but it's possible to do it. As you go to the right and down on this diagram, the value proposition simply isn't there. It's not that we couldn't get X, copper or gold plating out of a laptop computer or a cell phone, but the amount that's there is very, very small, and the cost of getting it out far exceeds the value of the component. So the take-home message here is that recycling is a great thing. We should do as much as we can and change manufacturing to allow it to be as easy as possible, but it'll never be 100% efficient. And even if it was, that wouldn't solve the entire problem. Okay. Another factor we need to consider is that many of these elements, particularly what we call the high-tech elements, are obtained as the byproduct of the mining of something else, the major commodity. So this diagram for the periodic table illustrates in bright red elements that we get almost all of them from the byproduct of production of something else. One example that's commonly used is the element tellurium, which is essential for many solar panels and energy efficiency operations, is almost entirely produced as a byproduct of the mining of copper. Okay, and so if you want more tellurium, raising the price of it's not going to change the amount, the availability of tellurium, because it's the copper mining that determines that. And if the price of copper hasn't changed, the amount of copper, more or less, is not going to change, and therefore the amount of tellurium is not going to change. So it's not simply a matter of letting prices determine how much is there and what the demand might be. It's a much more complex story, and this illustrates one of the concerns. Another concern is that elements are not evenly distributed around the world, okay, due to various geologic factors that we'll discuss more later. Certain elements are present in certain types of rocks that occur in certain countries. It might be a matter of the age of the rocks or the composition of the rocks. And so this graph illustrates for the periodic table elements that are mainly produced in a particular country. So you can see, for example, for Brazil, it's the major source of niobium in the world. And what's obvious from looking at this is that China is a major source for a lot of different elements. And this gets into the idea of supply chains. If an element is produced in lots of different countries, 20 different countries, then if the supply is cut off from one particular country, that's not really an issue. The other 19 could supply it. But if the supply is coming from a few countries or only one country, then you've got a real problem if for some reason that supply is interrupted. And it can be interrupted due to natural events like hurricanes or tornadoes or earthquakes, volcanic eruptions. All these things could interfere with it. Then you have economics and politics, things like tariffs, trade wars, not to mention real wars. So all these things can interrupt the supply chain, which is why people are spending a lot of time looking at the availability of where their mineral resources are coming from, how adequate they might be, and their vulnerability to interruption. This was brought to the fore in a study in 2008 by the U.S. National Academy of Sciences with this little diagram on the left, not because people hadn't thought about this before. This issue goes back centuries of people being concerned about it. But this diagram made it very easy for people to understand it. The two axes are the impact of a supply disruption and the risk of that happening. And so as you go to the upper right, things get more critical. They get more susceptible to being disrupted. And you can start plotting different elements on the diagram on the right part of this to sort of illustrate where they might fit on this risk reward scenario. And other people like the United States Geological Survey have developed a more quantified method of assessing criticality, looking at a combination of factors having to do with market dynamics and the growth of production and supply risk, world governance indicators. And all that is put together into a series of equations that allow us to measure the criticality and how it changes with time. So this is the periodic table again with a series of criticality indicator values, a time series over about 15 years. So you can see for each element, you got a little bar graph in there. And so for something like nickel, it's more or less constant, or aluminum. It's not really changing that much because these are widely available from many different countries. Whereas an element like lutetium in the lower left, or mercury, these have a very sharp upward slope indicating that they've become much more critical in recent times. We can also do some forward modeling to anticipate where we might need more of different types of resources. So this is a study of air conditioning units, which most people in certainly the US and in Europe take for granted, but in other climates that also are hot, such as most of India, Africa, lots of China, the increasing demand for air conditioning is just going to go up and up. And in particular, the new, very efficient air conditioners use permanent magnets that use certain elements. They're generally called rare earth elements. And one of them in particular is really needed for these permanent motors, and it's called dysprosium. And so we can both measure and model the growth of demand for air conditioning. And it's not too hard to figure out that within a couple of decades, the total amount of dysprosium needed just for air conditioners, not for all the other uses, is going to exceed current world production. Okay. Again, this doesn't mean we're going to run out of it, but it means that we're going to have to find new sources for it, and that this is one example of the confluence of technology needing elements either that we didn't use before or in bigger quantities than we used before. So where will those materials come from? Okay, so even though I've made it very clear there's very little danger of material exhaustion, there's a very real danger of supply disruption. Okay, and so that's something people are concerned about in this concept of criticality. And one simple way of defining criticality: critical means you need it, and strategic means you don't have it. So this is something that a lot of people are concerned about. Okay, another important point is that mineral resource discovery is not automatic. Okay, it takes time. Okay, the minerals don't jump out of the ground and say, "Here I am. I'm a big copper deposit. Come find me." Okay, it takes training. It takes very sophisticated techniques to try to find economic sources of various metals. And this is one area where training and education really is important, and that society as a whole is somewhat dropping the ball, is not putting nearly as much emphasis into that education and training so that we have the people with the skill sets to actually find the resources that we're going to need. Okay, even if you're successful with exploration, you need to understand that you can decide whether to mine something, but not where to mine it. Okay, so mineral deposits are part of nature. Okay, they occur in certain geologic environments, and we can decide whether or not we want to develop that, but we can't say, well, I want to develop it here in this country or in this state or this province, because it may not be there. Okay, so this is understanding geology and natural science. Another thing to consider is that even if you find a deposit, okay, it takes time to develop it. So if we go out tomorrow and we find the world's largest dysprosium deposit or copper deposit, and it's not going to instantly be in production. It's going to take at least several years to build the infrastructure, the roads, the buildings, the processing to get it out. And that's assuming that it's economic at that point in time. Some discoveries are of metals that need a higher price before you could actually put them into production, or they may need changes in technology or the way society uses them so that there's more of a demand to necessitate that deposit going in. So this diagram illustrates the discovery history of lots of deposits around the world for a variety of different elements, nickel, uranium, zinc, etc., when they were discovered, and then how long it took before they were actually put into production. So you can see at the present day, 2020 or 2021, since it's the new year, it's zero, because anything discovered today won't be in production for some period of time. And then as we go back, you can see it gradually expands, but some things might take 40 or 50 years before they're actually put into production, again, because needing certain prices or certain values of economics or technology to allow it to actually be put into production. So the various points that we need to consider that I've gone over. Number one, and this is really important, most people should understand it, but it needs to be said again. As world population and standards of living increase, we need new mineral resources. Okay, we simply cannot supply that increased need through other means. Okay, recycling, even if it's 100% efficient, cannot supply the entire need. And again, let me be clear. This is not that we shouldn't be doing as much recycling as we can. We should, and make it as efficient as we can. But even if it was 100% efficient, which is impossible, it still can't supply the entire need because of point number one, world population and standards of living. Okay. Same thing is true for being more innovative and efficient in manufacturing and technology. It can help, but it can't supply the entire need. So the concept of a circular economy, which is a fine concept, it can help, but it cannot supply the entire need. So the idea that an economy could be truly circular and that a growing population and rising standards of living could be met by somehow recirculating the material resources we already have simply is not valid. Okay? We're going to need new resources, and we need to do that in combination with everything else: efficiency, innovation, and recycling. So I'll leave you with a concluding statement that to do a complete life cycle analysis of mineral resources and their needs and their flow through society, we need to include both the upstream part, exploration, discovery, and production, as well as the downstream parts, the manufacturing, recycling, and disposal. And all of this needs to be developed on a foundation of education, training, and skill development. And although I think we're very good as a society doing that for the manufacturing and production part of the system, and the exploration discovery is well tuned, but the actual educating the next generation of people to do that is really lagging behind what we can predict will be the actual needs of society. So I will leave you with a plea for better education in the development of new resources, understanding of those resources, developing technology and efficiencies of scale, and subsequent speakers will go into various aspects of that. So I thank you for your attention and will be happy to answer questions when we get to that part of the presentation.
I'm Nelly Mutimeri, a geologist, STEM development practitioner, and an associate professor with the School of Mining Engineering at Wits University in South Africa. I'm the Mining Practice Director of Moot Consult, an advisory service in mining and minerals, advising governments, mining companies, and other entities on mining policy strategy and regulation. I'm interested in how the exploitation of minerals can be done in a just way and how it can contribute to social justice and human development. My part of this lecture that I'm sharing with Dr. Larry Maynard is from the perspective of social justice in mineral world. I'm building on what Dr. Maynard has very knowledgeably shared on the theme of earth materials as the foundation for development. He spoke about mineral demand and its connection to the economy and technology. I will be sharing with you some thoughts on the related socio-economic aspects of mineral development. I'm going to do this by sharing my thoughts on the following topics. Firstly, the history of mineral extraction from early human development. Secondly, where minerals come from. Thirdly, why minerals are important. And lastly, finishing off by delving a little bit into the subject of mining minerals and sustainable development. When thinking about how mineral extraction is linked to human development, the three periods I find really interesting are firstly the use of minerals in the early history of human development. Secondly, the growth in the demand for raw materials, which is closely linked to the rise of explorers from Europe and is linked to what I refer to as the Colonial project. And thirdly, where we are now and the trends for addressing mineral-related socio-economic issues. I think it is very telling that generally the accepted names for the ages of the development of humans are based on rocks and minerals. So you have the Stone Age, you have the Bronze Age, and you have the Iron Age. In my own part of the world, in Southern Africa, as indeed is true in many parts of the world, there is archaeological evidence that our ancestors increasingly used minerals as they developed. It is testament to the existence in the growth of geological, mining, metallurgical, and tool-making knowledge and skills. Depicted here is some of that evidence. In the first row, you have the world's oldest and first underground mine in what is now Eswatini. Then you have the iron smelting in what is now Limpopo province in South Africa. In the second row, you have a stone tablet found at an archaeological site in South Africa, which is said to be evidence of the early engravings of humankind. Implements, for example, this tool used for agriculture, also found at another archaeological site in Southern Africa. Then you have the gold artifacts from Mapungubwe. Mapungubwe was one of the most successful empires in Southern Africa and was linked to the Mutapa Empire of Great Zimbabwe. The current socio-economic issues that we experience now in the mineral sector are not just a present-day phenomenon. They may not have started with, but a lot of them are rooted in what I refer to as the early explorers and colonial project. In Latin America largely, but also in Africa and Asia, the most well-known, famous or infamous, depending on which side of the fence you're sitting, are the conquistadors, or the way-The conquistadors, conquerors in English. These were the knights and soldiers and explorers of the Spanish and Portuguese empires. During the Age of Discovery, conquistadors and their English equivalents, the German, French, Norwegian, and Swedish equivalents, sailed beyond Europe to the Americas, to Oceania, to Africa, and to Asia, conquering territory and opening trade routes. They brought colonialism to much of the world, starting from the 16th century. When they got to these foreign lands, they found empires and civilizations that existed there, for which minerals and their applications was a big part of those economies. And wresting controls of these lands and the minerals, as well as other natural resources like the ivory, shown here as seen in this depiction of slaves carrying ivory tooth to a merchant ship at Zanzibar seashore in 1844, opened up perhaps the darkest history of man, the most atrocious of which was the African slave trade, whose terrible, terrible impacts continue to play out today. In my neck of the woods, the manifestations of the colonial project with respect to mineral exploitation are evidenced by the Cecil John Rhodes Colossus in the late 19th century, which is associated with the plundering of minerals in Southern Africa. This included the early European diggings for diamond in what is now the Kimberley Big Hole in South Africa, and the colonization of what is now Zimbabwe and other areas of Southern Africa in search of minerals. The legacies of inequality and poorly developed nations, in my opinion, can be laid squarely at the foot of the colonial project. This is now history, of course, and a lot has changed. In the last couple of centuries, issues such as equity, social justice, sustainable development are now part of the discourse of mineral exploitation. One of the areas with respect to these new developments is optimal mineral resource exploitation. Many mineral-rich developing countries see this as a way to carve out a space in the mineral sector that allows them to realize the full potential of their mineral wealth. It is generally accepted that this starts with a good minerals policy. Such an optimal minerals policy would include fiscal regime and revenue management to enable efficient or optimal revenue collection and application to the priorities of the country, geological and mineral information management systems that generate important geological data, and its efficient management so that it's accessible to potential investors and other communities that want to use it for development. building human and institutional capacity for the management of the sector, and creating a pipeline of skills for the industry. For areas where artisanal small-scale mining is relevant, a strategic framework is required to manage the wide range of socio-economic and environmental challenges associated with the subsector, while at the same time utilizing its potential for livelihood and local development. Mineral sector governance that ensures equitable sharing of benefits is required. And with respect to linkages, investment, and diversification, what is required is a framework based on an understanding that minerals are a wasting asset, and it's important to create linkages that leave lasting positive legacy. Environment and social issues require a management framework that prevents and mitigates the negative impacts that are often associated with mineral extraction. To be able to have these optimal mineral policies requires that there be an understanding of the key challenges facing the country and the sector, that all the actors are identified so that the process is as inclusive as possible, so that it can lead to the formulation of a collective agenda addressing the needs of all stakeholders. And proper planning for implementation is obviously the ultimate thing required. Many developing countries are trying to play catch up with countries like Canada, Australia, the US, where such policies are supposedly having the desired developmental outcomes. However, it is important to take cognizance of the different developmental trajectories that these countries have. One of the areas that these mineral policies and the regulatory frameworks for actualizing them have to factor in is ensuring responsible mineral supply chains. These are meant to ensure that in the process of sourcing minerals, there is management of social, environmental, and economic aspects, and the supply chains are also managed through production data. And this is usually done through supply chain due diligence and sustainability schemes. The example given in this illustration is of metals like tin, tungsten, tantalite, and gold. However, the interest that began with diamonds also spread to many other minerals. There is growing interest in ensuring that sustainability is there throughout the supply chain. And this is because there are many regions of the world, particularly in developing countries, where strategic minerals are mined in conflict-affected and high-risk areas associated with human rights abuses and negative impacts on communities and the environment. A lot of the responses are trying to address the requirements of international protocols like the US Dodd-Frank Act and the EU Conflict Minerals Regulation. And the responses include good practice guidelines coming out of organizations like the OECD and industry standards like the World Gold Council Conflict-Free Gold Standard and regional frameworks like iCRAG and regional mineral certification schemes. At national level, the mineral policy and regulatory frameworks have to be aligned to this. What I've just shared is best thought of from the perspective of the sourcing of minerals that are inputs into the products that make our world go round. And it is important to understand that mineral extraction is a process that is a life mine cycle. It is important to know what types of operations are producing these minerals and the geographic sources. The life mine cycle illustration ensures that mining is a long-term investment which needs careful planning for. Exploration can be as much as 10 years, followed by design and construction, which may take up to another 5 years. Hence, there's a lead to get to production of about 15 years. And the life of mine can be as much as 100 years, with the first few years given to ramping up in production to get to break-even point. Once the deposit is depleted, the next stage is closure, which may be another 5 years. And lastly, there's post-closure, which to all intents and purposes should be for perpetuity. Hence the saying, mining is not for ceaseless. Let me hasten to say that this mining life cycle is for an industrial scale, or rather seen from an industrial scale mining project. For the artisanal and small-scale mining subsector, things happen quite differently. The ASM sector is often presented as a scaled-down version of industrial scale mining, which is often referred to as LSM, large-scale mining. And to some extent, this is true. However, the way mining is done in the two subsectors is very different. The main differences are with respect to who is involved, and in the case of ASM, it is usually local people. The operations are largely informal, and that is outside the law. Whereas with ASM, it is dominated by large multinational companies, many of which are foreign to the jurisdictions in which they operate. Though the minerals exploited by ASM are usually precious minerals like diamonds and gold, they also produce what I've referred to now as battery minerals or energy minerals like teeth and lithium. And the ASM sector also produces industrial minerals, construction materials, and gemstones. On the other hand, ALSM is into everything. However, it is important to note that in some developing countries, mineral production is actually dominated by developing the ASM. One of the issues that is important to note is the dynamic between ASM and LSM, which is often observed in developing countries and attracts a lot of attention from developing practitioners. This is the conflict. Some think this dynamic to be a result of competition for mineral resources. However, recognizing that for both subsectors, their legitimacy is not always driven from documented mining law. There is need for working coexistence models. However, this is something that current policies and legislative frameworks are still trying to grapple with. These photographs tell a story of how different ASM and LSM are from each other. On one side, you have simple rudimentary methods of mining and processing, minimal skills, low capitalization, and consequently low productivity. On the other hand, you have high levels of mechanization, high capitalization, high levels of productivity, and consequently less labor intensive. These differences between ASM and LSM present a big challenge for the regulator in any given country in trying to create a balance. One of the things that is very clear when we talk about where minerals come from is that a lot of them still come from the developing world. Here, this illustration is of the stats from Africa for 2016. And for me, the conundrum is that in spite of all this growth that is evident, Africa continues to be the least developed continent, with its young people braving the perils of illegal migration to Europe and other developed countries to escape poverty. The question is, what needs to change? Perhaps the earlier position of optimal national mineral policies is not enough. Maybe what is required is for the mineral-rich developing countries in Africa and elsewhere to be allowed to retain a greater share of the benefits from the extraction of the minerals, instead of just being a source of raw materials for the industrialized and industrializing countries. This requires a more level playing field to be created. And this is an important aspect of social justice in mineral wealth exploitation. This explains why minerals are important for social justice. It is because they are important, they are an opportunity for economic transformation through mineral-based industrialization, for livelihoods for rural communities, and also for the production of raw materials for local needs as seen in the context of developing minerals. This illustration from Dr. Paul Jordan shows how linkages around the extraction of minerals can lead to greater economic transformation beyond just the mining, processing, and selling of the commodity. Here, he refers to backward linkages, which are economic activities that a country can have around the inputs that go into the resource extraction activities, e.g., capital goods, consumables, and services. Forward linkages, which are the economic activities linked to the production of intermediate products and the manufacture of finished goods. Then you have fiscal linkages, you also have spatial linkages, and finally you also have knowledge linkages. These linkages are often considered only with respect to industrial scale mining. However, they are equally applicable to the ASM sector, with a further link to the concept of sustainable livelihoods. The sustainable livelihoods approach, which has been applied to many sectors, has been used to understand what needs to be done to support rural communities whose main natural asset is minerals. This is the case when we are dealing with the ASM sector. It is important to understand what livelihood assets need to be mobilized to ensure that the vulnerability of these communities is mitigated, while at the same time helping them to formulate the appropriate livelihood strategies so that they have sustainable livelihood outcomes. An important part of this is having the right policies and processes and institutions to influence access and control of these 5 asset categories. One can also see how this approach to looking at ASM would link into the discussion about mineral linkages, more so when one is trying to address the issue of wasting or depleting assets that needs to be transformed into other more sustainable assets. Lastly, on the issue of why minerals are important, I wanted to mention development minerals. This is a concept that has gained traction in the last decade or so. The term development minerals refers to minerals and materials that are mined, processed, and manufactured and used domestically in industries such as construction, manufacturing, and agriculture. Also, economically important close to the location where they're sourced from. They include industrial minerals, construction materials, dimension stone, semi-precious stones. In these last few slides, I would like to share with you a few thoughts and recent thinking on how ESG's mining and sustainable development goals are important. ESG standards and frameworks are all the rage in the mining and mineral sector. There are many schemes that many companies in the sector subscribe to, officially or aligned to in terms of their operations. The main criteria are with respect to taking care of nature, interactions with stakeholders, leadership, strategy, policy, and regulation. The UN Sustainable Development Goals capture the spirit of the ESG criteria. Hence, this mapping of the UN 17 SDGs to mining can provide insight into how socially conscious mining companies can determine where they sit with respect to the attainment of these goals by the world. What is indicated in this illustration is that mining has indirect and direct impact on the attainment of the SDGs, both positive and negative. It is therefore a provision of guidance on where enhancement and mitigation needs to happen. The mapping in this case had an industrial scale outlook. However, it is also important to look at the ASM sector separately. A recent analysis of the ASM sector is premised on formalization being at the root of all efforts to transform the sector. Hence, for each of these SDGs, it is important to see how ASM could have a positive contribution and how ASM formalization could help mitigate the negative impacts of the sector and enhance the positive impacts. Given the large numbers of people involved in ASM, for example, in Africa, it's as many as 9 million or more, one can see how this is important to the debate on mineral wealth and social justice. I would like to end by pointing out the key things that I think are important, or a couple of them at least, important in ensuring social justice with respect to the exploitation of minerals. The first is capacity building of the regulatory authorities of mining economies in the developing world. I think this is key to ensuring optimal use of the development dollars. Secondly, community development agreements should be the norm, and the reason that these communities bear the brunt of the negative impacts of mineral exploitation, and hence they should play a key role in how benefit sharing is done. And this, of course, must be empowered communities so that they have an equal footing in negotiating these community development agreements. Thank you.